Today, we're going to break down the engineering behind a single cable PoE solution that delivers both power and data to 4 cameras. Our client needs 4 PoE cameras mounted on a light pole in the parking lots. Running 4 separate Ethernet cables would be expensive and disruptive, and installing AC power at the pole would require trenching, permits, and high-voltage electronic work. Naturally, the question becomes, can we solve this with a single Ethernet cable? Standard Ethernet rounds are limited to 100 meters, which is about 328 feet, so our 300-foot round is still within the limit. But when power is involved, we also have to consider voltage drop and overall PoE power budget. Each camera might draw around 10 to 12 watts, so 4 cameras together could require roughly 48 watts. And power traveling over Ethernet is never perfectly efficient. Some is lost in the cable, and some is consumed by the intermediate devices. In PoE design, source power minus cable loss minus device overhead equals the remaining power available for cameras. And one important rule engineers follow is that never size a system for average load. You size it for the worst case scenario. To make this work, we need 2 pieces of hardware. First, an industrial PoE++ switch capable of delivering up to 90 watts on a single port using the IEEE 2.3 BT standard. That's roughly 3 to 4 times the power of a traditional PoE. The second device is a PoE pass-through switch, sometimes called PoE powered switch. This unit receives both power and data from upstream PoE connection and then redistribute that power to multiple PoE devices. In other words, one Ethernet cable comes in carrying power and data, and the switch internally distributes that power across the PoE output ports without needing any AC power supply at the pole. Now, let's look at the system architecture. Inside the control room, the PoE++ switch connects to the network, or NVR. One high-power port runs single Cat6 cable out to the light pole about 300 feet away. At the pole, the PoE pass-through switch receives both Ethernet traffic and power, forwards network traffic through its internal switching fabric, and distributes PoE to 4 connected cameras. Keeping all high-voltage AC inside the control room is an important safety decision. At the pole, everything runs on low-voltage PoE, which greatly simplifies the installation and reduces electronic risk. Alright, let's revisit the power budget with a more realistic calculation. Suppose the switch port outputs up to 90 watts. And after typical PoE standard losses and around 3 watts of the cable loss over 100 meter Cat6 round, we still have roughly 70 watts available. The pass-through switch itself may consume about 5 watts, leaving us around 65 watts for cameras. If each camera draws about 12 watts, the total load is around 48 watts, which still leaves comfortable safety margin. However, engineers also consider startup power. Many cameras draw more power when they first boot or when infrared LEDs, heaters, or motors active. A camera that averages 12 volts may briefly spike to 18 or even 20 watts. That's why it's important to leave extra headroom in power budget rather than designing right at the limit. Now let's build a system. In a control room, mount the PoE++ switch, power it up, and connect to the network or NVR. Choose one of the high-power PoE ports, typically PoE BD ports, and connect it to the long Cat6 run goes to the pole. It's also important to use high-quality pure copper Ethernet cable, because copper-clad aluminum cable can cause high voltage drop and unreliable PoE deliver over long distances. At the pole, mount the PoE pass-through switch inside the waterproof enclosure, ideally rated IP66 for outdoor protection. Once the uplink cable is connected, the pass-through switch powers on automatically because it draws its power directly from the upstream PoE switch. Then connect each camera to 4 PoE output ports. As the cameras powers up, you should see the link and the PoE LED's luminance on the switch. Back in the control room, open the NVR interface and verify that all 4 cameras are online. It's good practice to test the features like a pan, tilt, zoom, or night mode infrared LEDs because these functions can temporarily increase the power consumption. If a camera resides during those operations, it usually indicates that a power budget is too tight. Few practical engineering tips that worth remembering. Always use high-power PoE ports for long cable runs. Never push the pass-through switch to its maximum power budget. Leave at least 15 to 20% in margin. Use outdoor-rated short Cat6 or Cat6A cable when running lines through conducted outdoor environments. Plan for expansion. If you later need more cameras or another pole, you can replicate the same architecture with additional high-power PoE ports. By understanding the real-world power requirements, designing around the PoE standards, and carefully selecting the right hardware, we can turn what looks like a complicated installation into a clean, single cable solution. This approach works not only for parking lots, but also for campuses, warehouses, industrial sites, and permitted security installations. If you're dealing with a similar scenario, I'd be curious to hear how you would design the system. Share your thoughts in the comments below. And thanks for watching, and I will see you in the next video.